Hi, this is Dr. John Bergduff. This is the second of 3 videos in a sequence discussing the concept of inverses of functions. In the first video, we defined what we meant by the inverse of a function and looked at that definition really clearly to get some basic ideas. Now, the examples that we used in that first video were primarily sets of ordered pairs or mappings. But as we know, most of the time when we see functions that are defined by equations. And we want to explore what we mean by the inverses of one of those. So we're going to start with a recollection of the definition from the first video. And what you do is actually almost obvious. So here we go. Definition: given a function f, the inverse of f is the set of ordered pairs formed by reversing the coordinates of the ordered pairs of f. Every ordered pair is reversed. The first coordinate becomes the second coordinate becomes the first coordinate. Well, suppose that your function is defined by an equation and you want those ordered pairs to turn around. Well, the key thing that I said that you want to focus on is that every x becomes a y, every y becomes an x. Every first coordinate becomes a second coordinate, every second coordinate becomes a first coordinate. And that will make these steps make a lot of sense. So, if a function f is defined by an equation, to find an equation that defines f inverse, follow these 4 steps. First of all, just as a matter of convenience, and we're going to do several examples, replace the f of x by y. F of x means y. And this is the key step right here. I'm going to really highlight this one. Reverse the x and the y. If you want the ordered pairs to reverse, you simply reverse the x and the y in the equation. Now the rest of this turns out to be cosmetic. We solve the new equation for y, and then because the equation was given in function notation, we'd like the inverse to be given in function notation as well. But we're no longer looking at the original function, we're looking at its inverse. So we replace the new y by f inverse of x. Let's see how we apply those 4 steps for a few specific examples. So here's a nice simple one. Let f of x equal 4x plus 5. So that's a function defined by an equation. Find its inverse. Find the equation defining the inverse. Now, I want to ask you just a side question before we begin. I'm not just killing time. I've got a point that I want to make. Will the inverse be a function? Now, this I want to remind you from the first video that when you start with a function, the inverse might be a function too, or it might not. The key is whether the original function itself is 1-to-1. So really, this question is equivalent to asking, is the function f 1-to-1? And let's think about that function. Looking at its form, notice it's in the form y equal mx plus b. This is going to therefore be a straight line, but it's not a horizontal line or a vertical line. It's got a slope of 4 and a y-intercept of 5. To be 1-to-1, the graph would have to pass the horizontal line test. And if you consider a line that's neither vertical nor horizontal, just some other line, it will pass the horizontal line test. Therefore, is the function 1-to-1? Yes. And that means the inverse will be a function too. Okay, side point. Let's get busy. Let's actually find the equation that defines the inverse. Okay, so we have our function. The first thing that I suggest that we do is replace the f of x by y. Now, this is simply to make our work cleaner and easier. We don't get all tangled up in the f of x notation. It means the same thing. The second step is the most important one. This is where the inverse is actually created. In the equation, you reverse the x and the y. The y becomes x and the x becomes y. That act right there causes the ordered pairs to reverse. The x becomes the y becomes the x. So you switch the x and the y. And in a sense, you're really done. So you kind of do a happy dance right here and say, yes, I've got that. But we have two more steps that we're simply going to do for cosmetic case. Because we usually see equations solved for y and not for x, there's nothing wrong with this equation, but it would be just more convenient if it were solved for y. I hope I said that right a minute ago. We usually see equations solved for y. I may have said for x. Anyway, we want to solve this for y. That's the way we usually see it. So solving for y simply means get the y by itself. And if we think about getting the y by itself, we would first of all subtract the 5, because we can subtract the same thing from both sides of an equation, and the 5 minus 5 on the right would give me a 0, and then divide by 4 on both sides, because again, what you do on one side, you can do on, if you do the same thing on the other, the equation doesn't change, it's equivalent. So we have x minus 5 over 4 equals y, and it's perfectly fine to reverse the two sides of that equation so that the y is on the left where we more expect it to be. I just reversed the two sides. So I've now solved for the new y. And again, because the original equation was given to us in function notation, we'd like the answer to be in function notation too. But remembering that we're no longer talking about the original function, but its inverse, we want to replace the y by f inverse of x. And there you go. That is how you find the inverse of an equation defined, of a function defined by an equation. 1, 2, 3, 4. It's going to be a recipe that we will follow over and over and over again. Let's do some more. Here's another one. Let f of x equal the cube root of x plus 1. Find f inverse of x. Will f inverse be a function? So we just, from what we saw before, we're really asking, is the function f 1 to 1? Well, you might remember that the general shape from a much earlier part of the course, the general shape of a cube root function is sort of a sideways wiggle like that. And that shape would definitely pass the horizontal line test. So we're going to come to the conclusion that this function here is 1 to 1. And you might want to look back at our videos on graphs of basic functions. So the inverse will be a function, and that's interesting. Let's go through the steps. So step 1, replace f of x by y. That's y equal the cube root of x plus 1. Reverse the x and the y in the equation. Every y becomes an x, every x becomes a y. X equal the cube root of y plus 1. And again, that's the key step right there, so we do a little happy dance because this is the point where we've created the inverse. All right, but for cosmetic reasons, we don't want to leave it that way. We have right at the moment x equal the cube root of y plus 1. And we want to solve that for y, get the y by itself. Now, I can see that if I want to get the y by itself, I've got this cube root in the way, and it would sure be nice if I could get rid of that. Principle of balance says basically as long as you do the same operation on both sides of an equation, you're getting an equivalent equation, you're not changing the solutions in any way. I could get rid of a cube root by raising both sides to the third power. The cube root cubed would just be the quantity underneath, and you may remember doing equations sort of like this in one variable much earlier in the semester. X cubed is equal to y plus 1. Oh, and then to get the y by itself, we'll just subtract 1 from both sides. X cubed minus 1 equal y. And again, we're used to seeing the y on the left, so we'll just rewrite that. And that looked like it was going to be hard, but it turned out it really wasn't. And so our final step is always replace the y by f inverse of x. So f inverse of x is x cubed minus 1. Not too hard. 1, 2, 3, 4. Follow the steps. This is one of the few things in mathematics where you just follow a recipe and you're going to be just fine. A little bit more complicated function. This one you might recognize as a rational function. In particular, it is going to resemble in shape, if you look at the graph, y equal 1 over x, but the x plus 1 will cause a shift in the horizontal direction, and the minus 2 will cause a shift in the vertical direction, and the 3 on the top will create a stretch. You know, as far as knowing what the basic shape looks like, that doesn't really matter too much. We know, that this is going to basically be like y equal 1 over x, and that general shape is kind of like this. So you might remember this from a previous point in the class as well. And the question simply is, would that be 1 to 1? And yes, I believe that would pass the horizontal line test. So will f inverse be a function? Yes, it will. Okay. By the way, would it have been so horribly terrible if it weren't going to be a function? No, it wouldn't. But using function notation for the inverse would not be appropriate if the inverse were not a function. Well, let's go through the steps. That was an interesting little sidebar, but the important steps are 1, 2, 3, 4. Replace the f of x by y equal 3 over x plus 1 minus 2. Reverse the x and the y. Every y becomes an x. Every x becomes a y. So x equal 3 over y plus 1 minus 2. X equal 3 over y plus 1 minus 2. Let me just double check that I copied it right. Yep. Okay. And now we need to solve for y. Now, what strikes me here is that we don't really like having variables in denominators. It'd be really nice if we could just get rid of that. I think it might make sense first to add 2 to both sides of the equation. X plus 2 equals 3 over y plus 1. But then if only that fraction were not there, our life would be easier. I think it would be just fine, though, to multiply both sides by y plus 1. And again, this should remind you of things we've seen earlier in the course. With the goal, then, on the right, that the y plus 1s will divide out, and you'll have an equation that actually, frankly, looks a little bit on the nasty side, but it doesn't have any fractions. So that's better than nothing. And now we want to think about how we would get the y by itself. Well, we could kind of do almost the reverse of what we just did. The y would be more by itself if this x plus 2 were not in the way. So what if we divided both sides by x plus 2, which again is legal, and then my equation would look like y plus 1. The x plus 2's would divide out. Equals 3 over x plus 2. Oh, and then getting the y by itself is no big deal. I need a little bit more space. What we simply would do is subtract the 1. Y equal 3 over x plus 2 minus 1. And now we've got our equation solved for y. And finally, last but not least, replace the y by f inverse of x. And so even though this has become a good deal more complicated, the process is the same. Let's look back and remind ourselves of the original function. F of x equal 3 over x plus 1 minus 2. And the inverse is given by f inverse of x is 3 over x plus 2 minus 1. That's kind of interesting. One more example I would like to go through with you, and this particular equation is a little strange because there's an extra little doodad in it. So here's my function, f of x equal x minus 2 squared minus 3, x greater than or equal to 2. I want to talk about that in a minute. Let's just look at the equation that I've got for you first and think about that. So this will require us to, just for a minute, I want to think back to graphs of quadratic functions. You might recognize that that's what this is, and so its graph will be a parabola. But remembering some of our graphing techniques, the -2 right in here is going to cause the parabola to shift 2 units to the right, and the -3 on the end will cause it to shift down. If we focus on what happens to the vertex, which is ordinarily at the origin, that vertex will shift 2 to the right and 3 down and be right here. Ordinarily, the vertex would be at the origin. Now we shift it 2 units to the right and 3 down. Now the shape will basically be the same as the very basic parabola, y = x squared. And in particular, you can mimic that shape if you remember that that parabola, based from the vertex, there's a point 1 unit to the right and 1 unit up, and 1 to the left and 1 unit up, and therefore the graph looks something like this. It's a parabola. And there we go, something like that. Maybe a little less lumpy. Now, so what's interesting here? Notice that this function is not one-to-one. Now that's not a bad thing, but what it does mean is that its inverse will not be a function. A little trick we do sometimes when we have a function that's not one-to-one is we restrict the domain. We say, okay, that function is not one-to-one. What if we only looked at part of it? That's what this little x greater than or equal to 2 is doing. This is saying we're only going to look at and consider that part of the graph that is valid for values of x that are greater than or equal to 2. From here to the right. What that essentially does is it says we're going to throw away all of the graph that's to the left of 2 and only look at the part of the graph that's to the right of 2 for x greater than or equal to 2. And that's essentially throwing part of the function away. The fancy phrase is we're restricting the domain. But if you notice what that does is we create something that now does pass the horizontal line test, and therefore its inverse will be a function. And you might wonder, does that make it much harder to figure out what the inverse is? And the answer is no, it really doesn't hurt very much at all. Those of you taking trigonometry next semester, this idea of restricting the domain to create a one-to-one function becomes incredibly important when you're looking at functions like the sine function, the cosine function, and the tangent function. And if those words won't mean much to you right now, but later they will. Try to remember this idea of restricting the domain. All right, so we have all this, and again, let me just rewrite the function here. This is my function, f of x equal x minus 2 squared minus 3, and this restriction on the domain is an important part of the definition, so we don't want to lose it. We're going to go through the 4 steps. Now, I deliberately did not write down the 4 steps because what I'd like you to do is see if you can remember what they are. At each step, I'm going to pause and ask you to say to yourself, what's the first step we take? If you need to, you could pause the whole video and go back a slide or two and see. What is the first of the 4 steps? Okay, the first of the 4 steps is to replace the f of x by y. Replace f of x by y. And that's easy enough. You just take the f of x and you put a y there instead. So that step is not particularly dramatic. All right, I'm going to pause again. What is the second step? Okay, the second step is to reverse the x and the y. And if you notice how I've said this kind of dramatically in the other videos, it's going to be really, really important here. When we say reverse x and y, we mean that every x becomes a y and every y becomes an x. So The y becomes an x, the x becomes a y, and when I say every x becomes a y, I mean every x becomes a y. That includes this one over here in this little restriction. So instead of x greater than or equal to 2, we have y greater than or equal to 2. X equal y minus 2 squared minus 3, y greater than or equal to 2. Okay? Now, while I go to the next slide and rewrite the equation, I want you to be thinking about what our next step is. So I'm going to start by just copying the equation. You think. And I'm going to just double check that I copied it right. I did. So what was the third step? The third step is solve for the new y. Solve for the new y. All right, let's see how we can do that. So getting the y by itself, probably the first thing that's pretty obvious to do is add 3 to both sides, so that's not too hard. X plus 3 equals y minus 2 squared. If you don't mind, I'm going to go ahead and switch the left and right sides right now. Doesn't change anything, but I might make it a little bit easier. Oh, and you know what? As I do this, I do not want to forget this restriction. So at each step, I want to write down a reminder that y is restricted to be greater than or equal to 2. I think this step, the way I rewrote it, might make it easier to think about what you might do. You want to get rid of the square. And to get rid of the square, you can take a square root. You might remember the square root method way back at the beginning of the course. And you might remember a very important extra fact that when you do that, you don't just take the square root, you take plus or minus the square root. And again, we'll keep this restriction. We don't want to lose it. So getting rid of the square on one side, you say plus or minus the square root on the other side. Now it's not too hard to see what happens next. Add 2 to both sides, and I just think it would be prettier if I wrote the 2 up front. Here we go. Now I could jump right to the final step at this point, but I can also be very, very clever. I can actually do something to make this look a little bit better. Looking very carefully at the equation, notice that y is one of two things. It's either 2 plus the square root of x plus 3, or it's 2 minus the square root of x plus 3. If you add the square root of x plus 3, you're going to end up with something bigger than 2. If you subtract the square root of x plus 3, you're going to end up with something smaller than 2. Notice that in our restriction, we want the y's to be greater than or equal to 2. So that actually gives us a hint or a clue that we can actually pick one of the two signs. Solving the equation, they're both supposed to be there, but because of that restriction that we want y to be bigger than 2, we really would only want to be adding things to 2, not taking away things from 2. So I can do this. I can say, you know what? I'm committed to 2 plus the square root of x plus 3. And because I have thought about this restriction to throw away the minus, basically, I've really kind of used taking care of what the y greater than or equal to 2 is for. It's served its purpose. I could leave that out now, because if the equation says y equal 2 plus the square root of x plus 3, that's guaranteed to be a y that's bigger than or equal to 2. I don't have to write that anymore. I could leave it just the way it is. So that's a little bit tricky, and I hope that makes sense. But that gives me, that restriction tells me I get to pick one of those two signs. Now again, I'm going to go to another slide, and while I'm doing this, and I want you to think carefully about what the next step is. So this is buying you some time while I'm recopying the equation. All right, do you remember step 4? Step 4, very simply, is replace y by f inverse of x to get us back in function notation, and that is nothing more than this. All right, that was fun. Now, there's one little side thing I want to show you. When you read in your book, or try some of the homework in the book, you might see an example like this, or a question like this. Use the definition to show that the following two functions are inverses of one another. And if you look back, these are actually examples that we did before. We started with f of x equal the cube root of x plus 1 and ended up with x cubed minus 1. So you might say, oh, well, isn't that what we did? And really it is. When people use this phrase, it's often because they define inverses in a different way than I have done. I stated this little statement as an observation. Some people state this as the definition. I prefer to think of it as an observation, that if you have two functions, if a function and its inverse are both functions, then when you do the composition of the functions, you get x both times. Now, again, that's sometimes stated as a definition, but I recommend we use it as a check. So, what is f inverse of f of x? Remember that composition of functions means you take the first function, write a bracket, and then the second function. And then you look and see, well, what is f of x? F of x in this case would be the cube root of x plus 1. Now I'm believing that this thing g is the inverse, so that's what I'm going on right here. If I want g, let's say g of cube root of x plus 1, that means I want to go into that expression, the expression that defines the function g, or f inverse, and everywhere I see the x, I want to replace it by what I have in parentheses here. So that would be, what's in parentheses would be cube root of x plus 1 cubed, so I'm replacing the x by that, minus 1. And then if you take a cube root and you cube it, the radical goes away. You get x plus 1 minus 1, and you end up with x. If you end up with x, which is what you want, that sort of verifies that these might be inverses. You actually have to check it both ways. So f of f inverse of x, if you remember, that would mean f of f inverse of x, reading it from left to right. And my f inverse is my g, so that's x cubed minus 1. So I'm substituting in what I believe to be the inverse. And then I go back to my original function, and that's the cube root of x plus 1. But where I see the x, I write in what I have in parentheses. And simplifying that, under the radical, the negative 1 and the positive 1 add to 0. You get the cube root of x cubed, and the cube root of x cubed is x. If you perform the composition both ways, and both ways you end up with x, then those indeed are inverses. Again, some people use this as the definition. I prefer to think of it as just a way to check, and you can check your work at any point by trying this composition both ways and making sure you get x. Okay, hope that's all been helpful. One more video on this topic to go.